Guys, well, now that you've had a chance to see if you are a golden person in the activity today, let's talk a little bit more about that golden ratio that you needed to be if you were going to have a golden body. If that was one of the things that we looked at, if you're a golden person, we did that both by measuring the ratios of the body and also of the face. And obviously, you saw how that turned out. Let's talk more about that ratio that we were discussing. So, the golden ratio is one of the most famous numbers in all of mathematics. The ancient Greeks actually gave it mystical properties, called it the divine proportion. Over time, it also took on the name the golden number, and in modern times, the golden ratio, which golden ratio is what we will tend to use as our notation. Now, in order to write this using the classical Greek notation, they typically use the Greek letter phi, which sometimes pronounced phi, but the traditional Greek pronunciation is like the fees that you would pay for school or something like that, student fees. But FEE is kind of how you pronounce this Greek symbol. Again, some people will pronounce it as phi, but we'll go ahead and say phi for at least this section. Now, the golden ratio is an irrational number, so kind of like pi or like Leonard Euler's number E, if you are familiar with those, means that it can't be simplified into a fraction. It continues on as a decimal to an infinite number of places. You would never be able to finish writing it, even if you wrote it for the rest of your life. So for practical purposes, we're just going to use a decimal approximation. In fact, 1.618 is a pretty close enough number for the golden ratio for our purposes. Now, if you want to get a little bit more exact, the actual number for phi is 1 plus the square root of 5 over 2, which you might recognize from the Fibonacci numbers. That was part of our formula. You can disregard the note down here. I think it was misplaced from the previous section of notes. But you will recognize that phi, this 1 plus the square root of 5 over 2, was actually a part of Benet's formula. If you remember, Benet's formula was a formula that allowed us to calculate Fibonacci numbers without having to write out the entire sequence up to that number. And it turns out phi is actually a part of that. Now again, phi is approximately 1.618, but if you wanted the exact value for phi, that would be this number right here. All right. Now, the golden property is an important property that kind of goes along with that, which we will discuss that once I have a chance to restart OneNote real quick here. Thank you guys for your patience in watching the video. Hopefully it doesn't take too long to get it uploaded. There we go, cool. So the golden property, let's talk about that next. So say we had a goal, and our goal is to find a positive number where when you add 1 to it, you get the square of that number. Well, to solve that, let's first write it as a quadratic equation. So if you square a number, then it should be equal to that number plus 1. So to solve that, we're just going to rewrite it. So move over the x and the 1, and you'll get this equation right here. X squared minus x minus 1 is equal to 0. We can then solve that using the quadratic formula, and don't worry, I'm not going to make you do that, but I do want to at least show you it right here. And when you simplify it, you get 1 plus and minus the square root of 5 over 2. Now keep in mind, one of those solutions is negative. 1 minus the square root of 5 over 2 becomes negative 0.618. The other is the golden ratio, which is 1 plus the square root of 5 over 2. So you would use that as your number phi. In other words, phi is the only positive number with the property that when you add 1 to that number, you get that number squared. So it is the only positive real number that satisfies this property, that if you take phi and square it, that's the same as taking phi plus 1. We call this the golden property, and it's going to be an important property with both algebraic and geometric implications. We're going to look at the algebraic implications today in the context of the Fibonacci numbers, and then we'll look at some of the geometric implications on Friday when we talk about gnomons. So with the Fibonacci numbers, let's talk about how the golden property can help you to see those Fibonacci numbers. So we're going to use the golden property of phi squared being equal to phi plus 1 And we're going to use it recursively to compute higher and higher powers of phi. In other words, if we were to take that equation and multiply both sides by phi, so multiply by phi on both sides, then on the left side you would get phi cubed, and then on the right side make sure you would distribute and you would get phi squared plus 1. Then what you could do is you could replace phi squared with phi plus 1, because remember, phi squared is equal to phi plus 1, and that would give you this equation right here, which would then simplify to be this right here. In other words, phi cubed is equal to 2 phi plus 1. If you continue to do that, in the next part, if you continue to multiply by phi on both sides, you would have this equation right here, phi to the 4th power is equal to 2 phi squared plus phi. And again, replace phi squared by phi plus 1, and you'll find out that phi to the 4th power is equal to 3 phi plus 2. Now, if you continue to do that, what you'll start to notice is a pattern. So do it one more time. If we multiply the equation we just finished with by phi on both sides, so multiply by phi here and here, on the left side we'll get phi to the 5th, and on the right side distribute, and you'll have 3 phi squared plus 2 phi. Again, replace phi squared with phi plus 1, and you start to get a pattern. Notice that phi to the 5th power is equal to 5 phi plus 3. So now we have a pattern, and if we continued this, notice that phi to the 6th power is 8 phi plus 5, phi to the 7th power is 13 phi plus 8, phi to the 8th power is 21 phi plus 13, and so on. Notice that that right-hand side is going to be an expression which involves two consecutive Fibonacci numbers. The general formula that expresses higher powers of phi in terms of Fibonacci numbers is the following. That phi to the nth power is equal to the nth Fibonacci number multiplied with phi plus the previous Fibonacci number, which you can also see by looking at the ratios between consecutive Fibonacci numbers. In fact, here is an example of that. So you've got your column of Fibonacci numbers as well as the Fibonacci number that would have come before. And notice at first you just take 1 divided by 1 as just 1, 2, 1.5, and so on. And eventually they start alternating to the point where as you get to higher and higher values, notice that, remember, phi is 1.618 and then some more. Notice that the higher the numbers you get, the closer the ratio gets to phi. Kind of interesting stuff. So, as a final formula to give to you guys today, just describing that ratio, if you take a Fibonacci number and divide by the previous Fibonacci number in the sequence, you'll get an approximation to phi. The larger the value of n, the better the approximation. Alright guys, that is it for this video. In the next video, we'll look at some of the geometric applications of the Fibonacci numbers and the golden ratio. Until then, have a good rest of your day.